Howdy, howdy. Mr. Thompson here with a video math lesson. I'm going to talk about the converse of the Pythagoras theorems. The converse. So to talk about the converse, let's just review here. The Pythagorean theorem says, and this is very much a abbreviated version, if a triangle is a right-angled triangle, if it's a right triangle has a right angle, then we have the relationship with the sides that a squared plus b squared equals c squared. Okay, this is the original normal Pythagoras theorem, or Pythagorean theorem, as it's sometimes called. Okay, so to find the converse, let's talk about what a converse is. If you're familiar with logic and sort of proofs and things like this, the converse of a statement is when you switch the if and the then parts. These are known technically as the hypothesis and the conclusion. Okay, the hypothesis is the if part, the conclusion is the then part, and to get a converse of a statement, you just swap them. Okay, so the converse of the Pythagoras theorem, the Pythagorean theorem, starts, instead of starting with if a triangle is right angled, it starts with the a squared plus b squared equals c squared parts. So it says if in a triangle the sides have this relationship, okay, and again this is sort of an abbreviated version, but I'm not writing it all out in words. So if the sum of the squares of the sides of the legs of a triangle, the short sides of a triangle, are equal to the square of the longest side, then it turns out those are legs in a hypotenuse, and that this triangle is then a right triangle. So that's the converse of the Pythagorean theorem, the Pythagoras theorem. And basically it's sort of a way to test whether or not a triangle is a right triangle or not. You take the short sides, square them and add them up, and then square the longer side, and that tells you yes or no, is it a right triangle. So let's look at a couple examples. Are the following triangles right triangles? So we have a couple of triangles with some sides. Okay, so we'll start with part A. We have 6 and 8 and 10 for this triangle, so we're going to plug that into the Pythagoras theorem, and we get 6, so that's 6 squared plus 8 squared and 10 squared, and we want to sort of know, are these equal? All right, so I just put a question mark there. I'm not going to put an equals yet. Okay, so 6 squared is 36, 8 squared is 64, and 10 squared is 100. And 36 plus 64 does add up to 100. So this is a right triangle. Okay, we can verify, we can confirm. And if you want, you can put in a little symbol to say, yep, this is a right triangle. Okay, let's look at the next one, 4, 9, and 12. Okay, so we'll plug that into the formula for the theorem. 4 squared, 9 squared, and 12 squared. We don't know whether it's equal or not yet. 4 squared is 16, 9 squared is 81, and 12 squared is 144. 16 and 81 is 97, which is not equal to 144. So this is not a right triangle. Okay, it does not have a right angle at all. Okay, that's more or less the converse, but we're going to take this one step further and say, well, if it's not a right triangle, what could it be? Okay, and there's basically three options for what triangles can be. They can be acute, right, or obtuse. Acute triangles, as you may be familiar with, they're triangles with 3 acute angles. A right triangle is a triangle with a single right angle. The other ones would be acute. And an obtuse triangle is one that has a single obtuse angle, and then the other two would be acute. Okay, so we know if a triangle is a right triangle, we know that it's going to have this relationship, that the a squared plus b squared equals c squared. And for this exercise right now, for this concept, it's easiest to, I like to put the c squared first, which is always sort of allowed. C squared equals a squared plus b squared. And we'll kind of see why here in a second maybe. Okay, so if the c squared doesn't equal a squared or b squared, there's two options. It can either be, this c squared, the hypotenuse squared, can either be bigger or smaller. Okay, and one of those is for acute, one is right. And actually for acute, it's smaller. If c squared turns out to be less than a squared plus b squared, okay, then it's acute. And that's why I put c squared first, is because I'd rather use the less than symbol with acute. And then, of course, for obtuse, I'm going to use the greater than symbol if the, sorry, go back a second, that's a bit distracting. If the c squared is greater than a squared plus b squared, then that makes it obtuse, okay? So if you keep that c squared in the front, then it's easy to remember because greater than is obtuse, which is sort of bigger than 90. Less than is smaller, and it's means there's all the angles are smaller than 90, okay, making it acute. So this example that I'm putting up here is just a problem from the previous page, that 4, 9, and 12 that we just did. 97 is not equal to 144. It is smaller, right? 97 is smaller. The hypotenuse is bigger. The hypotenuse squared is bigger than a squared plus b squared, so that makes it obtuse. Okay, that was an obtuse triangle. Even though it didn't look like it, and I'm going to go back to that last page because that's an important part. This looks like a right triangle, okay? But in these problems, if you're given a drawing for the triangles, you just need to use the numbers and go by the numbers. You'll often see little disclaimers by these drawings, like not to scale or drawings not necessarily accurate or whatever, that kind of thing. Okay. All right, let's look at a couple of quick examples. Okay, more examples. And this is more often how you see these problems given. They just give you 3 numbers, okay? And these would be the 3 sides of a triangle. You know, and maybe 2 of them are the same, or maybe they're all the same. But you usually have sort of one bigger one, or if there's 2 that are the biggest ones, then either one of those can be the hypotenuse, or it can be the c squared. And you can start to see patterns and things like that, and these problems get pretty easy once you do a few of them. You can start to almost figure them out without even doing the calculation, but you should always do the calculation just to check anyway. Let's just walk through these really quickly. We got 6 squared plus 7 squared, and comparing that to 8 squared. Okay, so we get 36 for 6 squared, 49, and 64. So 36 plus 49 is 85, which is greater than 64. But we'll focus on the hypotenuse, the longest, what would be the hypotenuse, the longer side. It is smaller than 85. Okay, the c squared is less than a squared plus b squared, so that makes it acute. Okay. Next one, 10, 12, and 20. 10 squared plus 12 squared and 20 squared, so we get 100. 144 and 400. 100 plus 144 is 244, which is clearly less than 400. So the c squared is bigger. Okay, and you know, I guess I could have done these the other way to keep it consistent with my last page, but hopefully you can follow along that they were kind of doing things the other way around. But the point is, the c squared is bigger. That makes it obtuse. Okay. Last example, and I bet you can guess what the answer will be. We got 8 squared plus 15 squared and 17 squared, so 8 squared is 64. 15 squared is 225, and 17 squared is 289. Really good practice, really good idea. If you're studying this stuff, just to memorize these squares up to 20 is pretty easy to memorize. Even up to 25 is not too bad. And it just makes these problems quicker. So you should memorize those. If 15 and 17 are unfamiliar to you, then try to remember those. Write them down. Anyway, 64 plus 225 is 289, and 289, well, would you believe it, equals 289. So this is a right triangle. So there you go, the converse of the Pythagorean theorem, or Pythagoras theorem, along with determining whether the triangles are acute, obtuse, or right. Good luck. See you next time.